All right, welcome back. We did a lot of good progress. In the last few videos, we got all the way through VPNs. So now we're moving on to perhaps a bigger topic. It's going to be multicast. So this is kind of one of the topics I was dreading because it's probably the topic I have the least prior experience with. When I worked at the ISP, there was a department doing stuff with multicast, but I was mostly doing my experience is mostly with unicast. So this will be interesting. Let's get started. So good news too. I, at the request of a commenter, did NGVPN already. I did a whole series of videos on that. So I can start with PIM-SSM for this one. So that's really good news. Oh man. Okay, so I'll just do what I always do and make my notes documents. If I may. Okay, and then this is a new topic, so we're going to have a lot of changes. We need to make a whole new playlist, all that sort of thing. Oops. Okay, so the name of it is going to be Oops as a whole all the way up the chain. So, yep, we're doing multicast now, configuration troubleshooting. But yep, I already did that other one before, so some of the bureaucratic work is done. Okay, so we're good to go. We're going to have, so now we're going to have different things here. Multicast is going to be the tag. I think this is good for the tags. So yeah, let's do the classic way of setting this up. Or sorry, of getting help. We see what they've got in the help apropos. We do have a L2 VPN all set up, so maybe that can be used for learning multicast. As I said, this is probably the topic I have the least prior experience in. I'm not even sure if this was a part of the. I think it was part of the IP and the IS and all that. But it would have just been, these terms SSM, that sort of thing are familiar to me, but, okay, so pipe image. Oh, and it's not SSI, it's SSM, I believe. Yes. PIM-SSM. Here we go, perfect. So we've got topic routing options, examples, PIM-SSM. So if I go view private, edit routing options, we should have PIM-SSM somewhere in here. Maybe it's under multicast. Yeah. Okay, so now we have SSM, PM, PIM. We've got all our multicast options here. Okay. All right, so configuring PIM-SSM on a network. The following example shows how PIM-SSM is configured between a receiver and a source in the network, illustrated in network on which to configure PIM-SSM. So this graphic here, let's take a look. Okay, so looks quite a bit different than the network I've got. Hopefully I can just repurpose this network. We'll see though. This example shows how to configure the IGMP version to IGMP v3 on all receiving host interfaces. Number 1, enable IGMP v3 on all host-facing interfaces and disable IGMP on the FXP 0.0 interface router 1. So this example shows how to configure the IGMP version to IGMP v3 on all receiving host interfaces. Okay, so yeah, I'm not sure which are going to be host interfaces and which are going to be the other kinds of interfaces, but let's follow along. Yeah, you know what? Let's try to let's just read the most basic thing we can about multicast. I just want a better sense for it in general. Okay, so yeah, let's go to the official doc as soon as possible. Okay, multicast configuration overview. We've got a tech library here. Here we go. Multicast protocols user guide. This is the tech library we're gonna be using. So, yeah, let's just do overview, understanding multicast, and let's get the multicast overview because I don't even understand that too well right now. IP has 3 fundamental types of addresses: unicast, broadcast, and multicast. A unicast address is used to send a packet to a single destination. A broadcast address is used to send a datagram to an entire subnetwork. A multicast address is used to send a datagram. See, this is what I hate about documentation sometimes. Is a datagram the same as a packet? Does this mean that unicast sends packets and those other types send datagrams, and that unicast is not capable of sending a datagram? What is the difference between a datagram and a packet? See, I wish they would either say what the difference is between a datagram and a packet, or just say that unicast address is used to send a datagram. So a multicast address is used to send a datagram to a set of hosts that can be on different subnetworks and that are configured as members of a multicast group. A multicast datagram is delivered to destination group members with the same best effort reliability as a standard unicast IP datagram. This means that multicast datagrams are not guaranteed to reach all members of a group or to arrive in the same order in which they were transmitted. The only difference between a multicast IP packet and a unicast IP packet is the presence of a group address in the IP header destination address field. Multicast addresses use the Class D address format. So notes, okay, well, we're using MX, so I'm not going to remove that note. Individual hosts can join or leave a multicast group at any time. There are no restrictions on the physical location or the number of members in a multicast group. A host can be a member of more than one multicast group at any time. A host does not have to belong to a group to send packets to members of a group. Routers use a group membership protocol to learn about the presence of group members on directly attached subnetworks. When a host joins a multicast group, it transmits a group membership protocol message for the group or groups that it wants to receive and sets its IP, process, and network interface card to receive frames addressed to the multicast group. Comparing multicast to unicast, the Junos operating system, Junos OS routing protocol process supports a wide variety of routing protocols. These routing protocols carry network information among routing devices, not only for unicast traffic streams sent between one pair of clients and servers, but also for multicast traffic streams containing video, audio, or both between a single server source and many client receivers. So like, for example, a conference call. The routing protocols used for multicast differ in many key ways from unicast routing protocols. Information is delivered over a network by three basic methods: unicast, broadcast, and multicast. The differences amongst unicast, broadcast, and multicast can be summarized as follows: unicast one-to-one, from one source to one destination; broadcast one-to-all, from one source to all possible destinations; and multicast one-to-many, from one source to multiple destinations, expressing an interest in receiving the traffic. So not only is it from one source to multiple destinations, it's from one source to destination specifically requesting information from that source. It's not like unicast and broadcast where it's sent to a destination that doesn't necessarily want the traffic and that would have to set up an ACL to not receive, to toss it out. So it sounds like it has a little bit of extra kind of built-in security. Note, this list does not include a special category for many-to-many applications such as online gaming or video conferencing, where there are many sources for the same receiver and where receivers often double as sources. Many-to-many is a service model that repeatedly employs one-to-many multicast and therefore requires no unique protocol. The original multicast specification, RFC 1112, supports both the any source multicast ASM many-to-many model and the source-specific multicast PIM-SSM one-to-many model. So that's what we're going to be focusing on here. Source-specific multicast, and then PMM. Hopefully by the end of this document we'll figure out what that means. This is a really long document. I did not think it was this long. I'm just going to open the RFC here, and I might add that to the notes later. With unicast traffic, many streams of IP packets that travel across networks flow from a single source, such as a website server, to a single destination, such as a client PC. Unicast traffic is still the most common form of information transfer on networks. Broadcast traffic flows from a single source to all possible destinations reachable on the network, which is usually a LAN. Broadcasting is the easiest way to make sure traffic reaches its destinations. Television networks use broadcasting to distribute video and audio. Even if the television network is a cable television CATV system, the source signal reaches all possible destinations, which is the main reason that some channels' content is scrambled. Broadcasting is not feasible on the internet because of the enormous amount of unnecessary information that would constantly arrive at each end user's device, the complexities and impact of scrambling and related privacy issues. Oh, that's interesting. So it looks like when you get scrambled content from your cable company, the reason for that is because there's no way for them to send the signal to specific paying customers. So instead of just not sending you the signal, they say, okay, well, here's what you get. You get a scrambled signal, and if you want to actually see the actual signal, you got to pay us to unscramble it. So you're not paying to actually get the channel, you're paying to get a clear signal to the channel. Whether or not you get the signal to the channel is not something that the technology supports, because it has to be broadcast out to all destination. And the technology is cable television, so something like internet, all this stuff, these are different technology, much more advanced. But I'm thinking back, I was probably in like 4th grade, the last time I saw or heard of a scrambled cable channel. So technology has moved on, but that I've always kind of wondered about that, like why are these scrambled channels coming in? And the reason is because the cable provider can't determine whether or not you get the channel. All it can do is determine whether or not you can see the channel clearly. So that's what you're paying for. Alright, so multicast traffic lies between the extremes of unicast, one source, one destination, and broadcast, one source, all destinations. Multicast is a one source, many destinations method of traffic distribution, meaning only the destinations that explicitly indicate their need to receive the information from a particular source receive the traffic stream over an IP network, because destinations, clients, do not often communicate directly with sources, servers. The routing devices between source and destination must be able to determine the topology of the network from the unicast or multicast perspective to avoid routing traffic haphazardly. Multicast routing devices replicate packets received on one input interface and send the copies out on multiple input interfaces. In IP multicast, the source and destination are almost always hosts and not routing devices. Multicast routing devices distribute the multicast traffic across the network from source to destinations. The multicast routing device must find multicast sources on the internet, send out copies of packets on several interfaces, prevent routing loops, connect interested destinations with the proper source, and keep the flow of unwanted packets to a minimum. Standard multicast routing protocols provide most of these capabilities, but some router architectures cannot send multiple copies of packets and so do not support multicasting directly. Okay, so next step is IP multicast uses. Multicast allows an IP network to support more than just the unicast model of data delivery that prevailed in the early stages of the internet. Multicast, originally defined as a host extension in RFC 1112 in 1989, provides an efficient method for delivering traffic flows that can be characterized as one-to-many or many-to-many. Unicast traffic is not strictly limited to data applications. Telephone conversations, wireless or not, contain digital audio samples and might contain digital photographs or even video and still flow from a single source to a single destination. In the same way, multicast traffic is not strictly limited to multimedia applications. In some data applications, the flow of traffic is from a single source to many destinations that require the packets, as in a news or stock ticker service delivered to many PCs. For this reason, the term receiver is preferred to listener for multicast destinations. Although both terms are common, network applications that can function with unicast but are better suited for multicast include collaborative groupware, teleconferencing, periodic or push data delivery, stock quotes, sports scores, magazines, newspapers, and advertisements, server or website replication, and distributed interactive simulation, DIS, such as war simulations or virtual reality. I've never seen a war. Virtual reality, I can't imagine. Wow, okay, I guess a war simulation seems almost as complex as virtual reality. Any IP network concerned with reducing network resource overhead for one-to-many or many-to-many data or multimedia applications with multiple receivers benefits from multicasts. If unicast were employed by radio or news ticker services, each radio or PC would have to have a separate traffic session for each listener or viewer at a PC. This is actually the method for some web-based services. The processing load and bandwidth consumed by the server would increase linearly as more people tune in to the server. This is extremely inefficient when dealing with the global scale of the internet. Unicast places the burden of packet duplication on the server and consumes more and more backbone bandwidth as the number of users grows. If broadcast were employed instead, the source could generate a single IP packet stream using a broadcast destination address. Although broadcast eliminates the server packet duplication issue, this is not a good solution for IP because IP broadcasts can be sent only to a single subnetwork. The IP routing devices normally isolate IP subnetworks on separate interfaces. Even if an IP packet stream could be addressed to literally go everywhere, and there were no need to tune to any source at all. Broadcast would be extremely inefficient because of the bandwidth strain and need for uninterested hosts to discard large numbers of packets. Broadcast places the burden of packet rejection on each host and consumes the maximum amount of backbone bandwidth. For radio station or news ticker traffic, multicast provides the most efficient and effective outcome, with none of the drawbacks and all of the advantages of the other methods. A single source of multicast packets finds its way to every interested receiver. As with multicast, the transmitting host generates only a single stream of IP packets, so the load remains constant whether there is one receiver or 1 million. The network routing devices replicate the packets and deliver the packets to the proper receivers, but only the replication role is a new one for routing devices. The links leading to subnets consisting of entirely uninterested receivers carry no multicast traffic. Multicast minimizes the burden placed on sender, receiver, and network. Or sender, network, and receiver. I don't know why I flipped those. Oh yeah, so there's a whole bunch of terminology, so hopefully this will help me. Yeah, man, like, I mean, I'm tempted to keep reading because this is all new to me, but at the same time, I'm very, very rapidly running out of time and reading things that aren't going to help. And not only that, this is a hands-on exam, so I need to be able to do it. I mean, the concepts, that's one of the things behind this channel, concepts, not commands, but okay, so let's keep reading. So this is IP multicast terminology. Multicast has its own particular set of terms and acronyms that apply to IP multicast routing devices and networks. Figure 1 depicts some of the terms commonly used in an IP multicast network. In a multicast network, the key component is the routing device, which is able to replicate packets and is therefore multicast capable. The routing device in the IP multicast network, which has exactly the same topology as the unicast network is based on, use a multicast routing protocol to build a distribution tree that connects receivers preferred to the multimedia implications of listeners, but listeners is also used to sources. In multicast terminology, the distribution tree is rooted at the source. The root of the distribution tree is the source. The interface on the routing device leading toward the source is the upstream interface, although the less precise terms incoming or inbound interface are used as well. To keep bandwidth use to a minimum, it is best for only one upstream interface on the routing device to receive multicast packets. The interface on the routing device leading toward the receivers is the downstream interface, although the less precise terms outgoing or outbound interface are used as well. There can be 0 to n-1 downstream interfaces on a routing device, where n is the number of logical interfaces on the routing device. To prevent looping, the upstream device must never receive copies of downstream multicast packets. Okay, so I didn't see anything about PMM yet. Routing loops are disastrous in multicast networks because of the risk of repeatedly replicated packets. One of the complexities of modern multicast routing protocols is the need to avoid routing loops, packet by packet, and much more rigorous. All right. What we got here?
Rigorously.
Rigorously. Why is it not playing? I'm muted. Rigorously. Yeah, rigorously. And much more rigorously, I was trying to say rigulous. I was trying to put a U instead of the O here. Rigorously than in unicast routing protocols. Reverse path forwarding for loop prevention. The routing device's multicast forwarding state runs more logically based on the reverse path from the receiver back to the root of the distribution tree. In RPF, which stands for reverse path forwarding, every multicast packet received must pass an RPF, reverse path forwarding check, before it can be replicated or forwarded on any interface. When it receives a multicast packet on an interface, the routing device verifies that the source address in the multicast IP packet is the destination address for a unicast IP packet back to the source. If the outgoing interface found in the unicast routing table is the same interface that the multicast packet was received on, the packet passes the RPF check. Multicast packets that fail the RPF check are dropped because the incoming interface is not on the shortest path back to the source. Routing devices can build and maintain separate tables for RPF purposes. Shortest path tree for loop prevention. The distribution tree used for multicast is rooted at the source and is the shortest path tree, SPT, but this path can be long if the source is at the periphery of the network, providing a shared tree on the backbone as the distribution tree locates the multicast source more centrally in the network. Shared distribution trees with roots in the core network are created and maintained by a multicast routing device operating as a rendezvous point, RP, a feature of sparse mode multicast protocols. So I know that there's sparse mode and there's dense mode. So this probably stands for sparse mode. So sparse mode is going to be a whole topic. Administrative scoping for loop prevention. Scoping limits the routing devices and interfaces that can forward a multicast packet. Multicast scoping is administrative in the sense that a range of multicast addresses is reserved for scoping purposes, as described in RFC 2365, administratively scoped IP multicast. Routing devices at the boundary must filter multicast packets and ensure that packets do not stray beyond the established limits. Multicast leaf and branch terminology. Each subnetwork with hosts on the routing device that has at least one interested receiver is a leaf on the distribution tree. Routing devices can have multiple leaves on different interfaces and must send a copy of the IP multicast packet out on each interface with a leaf. When a new leaf subnetwork is added to the tree, that is the interface to the host subnetwork previously received no copies of the multicast packets. A new branch is built. The leaf is joined to the tree and replicated packets are sent out on the interface. The number of leaves on a particular interface does not affect the routing table. The action is the same for one leaf or 100. Note on Juniper Networks security devices, if the maximum number of leaves on a multicast distribution tree is exceeded, multicast sessions are created up to the maximum number of leaves, and any multicast sessions that exceed the maximum number of leaves are ignored. The maximum number of leaves on a multicast distribution tree is device specific. And I have some tools here that my legs are feeling really in need of these massage tools I have. Okay. All right, so when a branch contains no leaves, because there is no interested hosts on the routing device interface leading to that IP subnetwork, the branch is pruned from the distribution tree and no multicast packets are sent out that interface. Packets are replicated and sent out multiple interfaces only where the distribution tree branches at a routing device, and no link ever carries a duplicate flow of packets. Collections of hosts all receiving the same stream of IP packets, usually from the same multicast source, are called groups. In IP multicast networks, traffic is delivered to multicast groups based on the IP multicast address or group address. The groups determine the location of the leaves, and the leaves determine the branches on the multicast network. IP multicast addressing. Multicast uses the class D IP address range, and this should look familiar because we know that the EIGRP and the OSPF hello messages are in this range because they are multicast. I probably even still have it in my table here if I do show protocol OSPF. Boom, we see that range here, 255.0.0.5, because this is a multicast address when I do a Wireshark capture to look for the OSPF hellos. They're going to be sent to that address because they are multicast. So if I had like a hub or a switch here and multiples, that's why I don't need like an extra VLAN for every neighborship, the way I did here in my L2 VPN sites. Class D addresses are commonly referred to as multicast addresses because the entire classful address concept is obsolete. Multicast addresses can never appear as the source address in an IP packet and can only be the destination of a packet. Multicast addresses usually have a prefix length of /32, although other prefix lengths are allowed. I don't know why you would need it though, because it's multicast. Multicast addresses represent logical groupings of receivers and not physical collections of devices. Blocks of multicast addresses can still be described in terms of prefix length and traditional notation, but only for convenience. For example, the multicast address range from 232.0.0.0.0 through 232.255.255.255.255 can be written as 232.0.0.0/8 or 232/8. Internet service providers, ISPs, do not typically allocate multicast addresses to their customers because multicast addresses relate to content, not to physical devices. Receivers are not assigned by their own multicast addresses, but need to know the multicast address of the content. Sources need to be assigned multicast addresses only to produce the contents, not to identify their place in the network. Every source and receiver still needs an ordinary unicast IP address. Multicast addressing most often references the receivers, and the source of multicast content is usually not even a member of the multicast group for which it produces content. If the source needs to monitor the packets it produces, the monitoring can be done locally, and there is no need to make the packets traverse the network. Many applications have been assigned a range of multicast addresses for their own use. These applications assign multicast addresses to sessions created by that application. You do not usually need to statically assign a multicast address, but you can do so. Alright, so multicast addresses. Multicast host group addresses are defined to be the IP addresses whose high order 4 bits are 1110, giving an address range from 255.0.0.0 through 239, because you can have this, oh no, you can't have this one. Oh wait, no, because you've got 4 other bits that can all be on. So if you turn this one, you have 240, but if you turn the rest of them on and this one off, you've got 239. These addresses are referred to as Class D addresses. The Internet Assigned Numbers Authority, IANA, maintains a list of registered IP multicast groups. The base address 224/8 is reserved and cannot be assigned to any group. The block of multicast addresses from .1 through .255 is reserved for local wire use. Groups in this range are assigned for various uses, including routing protocols and local discovery mechanisms. The range from 239 to 239-1 is reserved for administratively scoped addresses. Because packets addressed to administratively scoped multicast addresses do not cross configured administrative boundaries, And because administratively scoped multicast addresses are locally assigned, these addresses do not need to be unique across administrative boundaries. Okay, so layer 2 frames and IPv4 multicast addresses. Oh man, there's just so much. There's so much just in this overview. I was tempted to like just stop, but I've only got like 10 minutes. There's just so much. Oh, here we go. So we're learning about PIM-SSM. So we're learning about, is it sparse mode? Is this it? Oh, I remember, yeah, I studied this before. I've read this all before. Yeah, so this is what we're going to learn about specifically. PIM, source-specific multicast. Enhancement to PIM sparse mode that allows a client to receive multicast traffic directly from the source without the help of an RP. Used with IGM-EV3 to create a shortest path tree between receiver and source. So let's try to keep on topic more. Like, you know, I think it's a good idea to go and read everything word by word, but I just don't have time for that, unfortunately. Okay, so hopefully we'll get some related documentation here. We can include the RFC in the notes, even though I'm not going to use it. Here we go. Configuring source-specific multicast for draft Rosen multicast VPNs. And then we also have, so that's it, yeah. So I think this is going to be the example I'm going to do. Yeah, this is going to be it. Perfect. So I'll need to be doing this in the next video though. This video, let's just see if there's, well, you know what I can do in this video? I can like wipe out, you know, the lab, all that sort of thing. Source specific. Let's see if we get any matches for source specific. Or PIM or SSM. Here we go. Yeah, so we got more examples here. I should have just read this. Whoops, my bad. Yeah, I should have been focusing on this instead of just the overview. Okay, so let's figure out why we need to use it. An environment where many sources come and go, such as for video conferencing service, ASM is appropriate. However, by ignoring the many-to-many model and focusing on the one-to-many source-specific SSM model, several commercially promising multicast applications, such as television channel distribution over the internet, might be brought to the internet much more quickly and efficiently than if full ASM functionality were required of the network. So there's no need for shared trees or RP mapping or for RP to RP source discovery. Okay, it looks like we've got a lot of examples here. We've even got examples within examples. Yeah, it'd be nice to just simplify it and do like these examples. Yeah, so you know what I'm going to do is just make, because I've only got like 10 minutes. So we're going to gather anyone that looks pretty good. We're going to go with that. So These are probably, hopefully all the same. Yeah, these are the same. Okay, so let's go with configuring source-specific multicast groups. Okay, so we'll be doing this one in the next video. The after work video. Then what's this one? This is configuring PIM-SSM on a network. Yeah, so it's the same one as this. But it's just listed individually. Okay, but we'll list them all individually. Okay, SSIM and mapping. This looks kind of difficult. Yeah, we'll list them individually and then cross them off one by one in the afterward video. It looks like it's going to be pretty easy. It's only going to require 1, 2, 3, 4 routers. So that's something I can do as well once I paste all these in here. Yeah, because it looks like they're all going to require this sort of topology. So I can I can break apart what I've currently got up there and just make that topology. At the very least, I can wipe. I mean, it's going to be more complicated here, but even here, it looks like it's pretty much the same sort of topology. Okay, so yep, here's all the documentation I'm going to do in the next video. So let's pull up one of those and see if I can save myself some work. And here's the OSPF hello messages to the multicast address I just wanted to point out. Okay, so we won't need the Cisco anymore. We won't need the icons and the squares anymore. Alright, and now we can open all this and yeah. And one thing I can even do, because it's calling for 4 routers, and I've got 6, 7, 8 routers, I can set up 2 topologies and we can look at the differences more clearly. I guess I don't completely regret reading all that documentation, but I do need to be very, very concerned about how much time I have, so continuing to read it I think would just be a bad idea. right. Oops. For some reason, oh, okay. I see. This is identical to the other one. I'm surprised it showed that it had configuration. But anyways, this should commit. I do have a 1 o'clock meeting, so I've got to make sure I'm conscious of that. But I think I'll have time to just rearrange the icons, get rid of all the links. That's going to need to happen. Okay, I don't need the labelings right now. Oops, I do need the icon. There we go. All right. All right, and then let's just rearrange the routers. So we've got 1, 2, 3, and 4, so we'll do that. 1, 4 is going to be up here. Okay, 2 is right here. And then 3 is over there. Okay, and then we'll do a similar topology here. So if there's multiple kinds of flavors of configuration, we can compare them. So 5, 6. Oh, what happened to 7? Where's 7? Okay, I don't see a 7, but okay, let's just go with 8. And then 9, and I'm not sure what happened with 7, but we'll figure that out in the after work video. So thanks for watching, and stay tuned for the after work video.